Great. We'll continue with the talk, which will be given in person, as you can see. Command F, can you try Command F? So this talk will be about coarse-grain stochastic reaction networks. It will be given by Albin Salazar.
Okay.
Is that okay?
Yes.
Can everyone hear me? And then I put this here. Okay, so yes, thank you for the introduction and thank you for the opportunity to present here today. So what I would present to you today is a generic framework to coarse-grained stochastic reaction networks. My name is Albin Salazar, and this is work done in collaboration with Jerome Feret, who so happens to be also my supervisor. So I would say that I think that I am one of the few biologists here at this conference, so please bear with me. Okay. So I would begin by giving a general outline. So the presentation is split into 5 parts. I will discuss the motivation and transition into a case study to provide intuition. Then I will introduce the generic framework. After that, I will transition into a second case study and then conclude. And so what we tend to focus on is the application of discrete models in biology. But what we care about more is really the understanding the mathematical foundation of discrete models or different types of modeling paradigms in general. And what we will focus on today is on assessing the type of behaviors that can emerge from logical models. Okay? So one specific type of logical model is Boolean networks. And these type of modeling frameworks are very popular in biology because they have proven to be successful. Okay? So you can imagine that you can build a Boolean network model to essentially capture the dynamics of biological systems. And what happens is that when you increase the number of variables, you get a state explosion of different possible behaviors that can emerge from your Boolean network model. And then you tend to make some assumptions about state space behaviors that don't really have any, let's say, any rigorousness in the way that you evaluate these behaviors, okay? And so what we would like to propose is to use abstract interpretation, which is a tool that has proven successful in approximating several mathematical structures. And we would like to abstract the behaviors that emerge from the reaction networks from a more formal level of representation. And so the menu of the day. So what we would like to do is to formally reason on the type of behaviors that can emerge from reaction networks. After which we would like to abstract them by intervals. So we use the interval lattice domain that has been proposed by Couzot and Couzot. After which we would then like to propagate probabilities from the reaction network into the abstract transition system. And what this will allow us to do is to measure competition between pairs of abstract transitions, right? And so this will allow us to then investigate the type of behaviors that are omitted in the logical models by assigning to abstract transition probabilities and being able to say which kind of behaviors are more probable than others rather than just neglecting certain behaviors. Okay? And so we begin with our first case study, which is the birth and death model. It's a one-dimensional system. It's modeled by 2 reactions. In the first reaction, you have a production of a molecule A. In the second, you have a degradation of a molecule A. This occurs at 2 different speeds. I will refer to these speeds as propensities. And I would like to show you how a logical model is derived. Okay? And so it is often used the René-Thomas principle, which means that if you evaluate the variable along its dimension, it will converge to a stable fixed point, or they call it an attractor. Okay? So the way that you would represent the amount of A is using implicit representation. So you would use, for example, low, medium, and high. So these respectively represent abstract intervals. Okay? And so what you would do is you would start on the left-hand side, which is you build your directed graph. You show how A is being regulated. So here it's positively and negatively. Then you would derive a logical function to capture this dynamics, so that depending on what is the value of A, you will converge towards the interval that is most stable. So in this example, that interval is when the value of A is equal to 1. And then you can imagine that when you compute the transition system using this logical function, if you are below 1, you will go up. If you are above 1, you will go down. And that is captured in the transition system. But what you can see immediately is that the transition system captures the behaviors that we expect. However, it doesn't capture the intrinsic behavior of the reaction network, which essentially you should be able to go back and forth because of the opposite behaviors that are in the reaction network. Okay? And so what we would like to do is to begin from this reaction network and use chemical principles. Okay? So what we can do is from this reaction network, we can derive probability functions. So we can define a discrete time Markov chain. And you can see that in these probability functions, so the way that you derive these probability functions is that you take the propensity of one reaction and you divide it by the propensity of all the reactions in the reaction system. So here we have 2. Okay? And so after which you can imagine the concrete transition system as a one-dimensional line. And so if you start from the empty set, as you go towards the right, you get several birth events. As you go towards the left, you get several death events. Okay? And you can imagine different combinations of the different types of reaction events in this reaction network. And what you can immediately see is also that the value of A is updated at each transition. Okay? So this is one important point to note. And so what we would like to obtain first is something in the bottom diagram, which is a non-deterministic abstraction. Here we use non-overlapping intervals. So what we do is we partition the values of A into intervals. These intervals do not overlap, which means that consecutive intervals do not share any common values. And what we would like to do later is to then reintroduce probabilities by reasoning on the concrete transition system. Right? So we want to compute probabilities to go from one interval to the other. Okay? And another important thing to note is that if you remove reversible transitions here, you get something that's very similar to the logical model scenario. Okay? But in our framework, we introduce reversible transitions. Okay? And so we do exactly that. So we reason with the concrete transition system. We get a coarse-graining of the sort. Okay? So what we have here is 5 different intervals on the left-hand side, 4 intervals on the right-hand side. Each interval represents a range of values of A. Okay? You can transition from one interval to the other if you exit your current interval. Okay? So you have 2 possible scenarios. You can either, so if we take the blue interval, for example, which represents a range of values between 10 and 14, you can exit your upper bound, so you can reach a value of 15 and go from blue to yellow, or you can exit from a lower bound, so you can either go from blue to red. Okay? So the reason that we duplicate the intervals here is to distinguish whether we enter from below or from above. So at this point, what we want to do is to reintroduce probabilities into this abstract transition system and see where the general trend of the dynamics of the birth and death model will converge to. Okay? Which interval will converge to. Okay? So we do this accordingly. So what we do is we denote capital Q as a set of states. So a particular state is a mapping of the variable A to a value of 13. So you can imagine that in the previous example, this was in the blue interval. And what you can do is define capital G to be a set of zone of interest you can think of. Okay? So it's a set of zone of interest, and so you can imagine that's 2 particular zone of interest that you're interested in is when you reach the yellow interval or when you reach the red interval. So it's when it's those concrete states such that the value of A is either in the new interval or it's in the red interval. Okay? And a particular zone of interest is when the value of A, for example, is in the yellow interval. Okay? And so what we can obtain from this is the following proposition. So we can compute the probability to reach a particular interval first, accordingly. So if you are already in the zone of interest, then your probability is 1. You don't have to do much. If it's in another zone of interest that you are not interested in, then that probability is equal to 0. And if you're outside of this zone of interest, you can converge using, you can converge towards this interval, You can compute the probability to reach this particular zone of interest recursively by looking at the several sequences of transitions that you take to reach this particular zone of interest. Okay? However, for the birth and death model, we can obtain a closed form solution. If you are curious how we obtain this, look at the paper or come speak to me after. So what we do is, using a closed form version of this proposition, we can compute exactly the probability to reach a particular interval prior to the other. Okay? So I will use my example again. Okay? So I will start from the blue interval. So my probability to go from the blue interval to the yellow interval is 0.47 in this example. my probability to go from the blue interval to the red interval is 0.53. And you can imagine that if you capture the appropriate dynamics of the system, you should converge towards the interval that contains the steady point of the system. Okay? So what we do is that we start from the reaction network. We compute the steady state values. So this is done by setting the propensities of the two reactions equal to each other and identifying the point at which the two reactions are balanced. And then you abstract this value. And so that value is contained here in the maroon interval. So it's when the value of A is equal to 20 to 24. Okay? And so you should expect that each abstract transition should converge towards the interval that contains the steady state value. Okay? And what you observe in this transition system is that you don't get exactly the dynamics that you expected. Yeah?
Can you help me understand what in the transitions you were just talking about, the 0.47 from blue to yellow and the 0.53?
Exactly.
It seems to say that with probability 1, you will exit the blue interval. What am I missing?
With probability 1?
That you will exit the blue interval. Because 0.47 plus 0.53 is 1.
Yes. So you have two possible transitions, right? You can either exit your interval from the upper bound, or you can exit the interval from the lower bound. And so the sum of these probabilities should be equal to 1.
I guess what I'm missing, though, is aren't there transitions that stay within the blue interval? I mean, aren't there reactions that keep you within the blue interval?
So there are reactions that can keep you in the blue interval, but you cannot stay in this interval forever. Does that answer your question? Okay. So you can imagine that you can have several types of reactions that can occur. And if your value is between 10 and 14, when you abstract the value of the amount of A after some reaction, it will either be in the blue interval, or it can exit from below or exit from above. Yeah.
So I guess the system then is not modeling every reaction that occurs, but only
the general trend of the
Gotcha.
system.
Okay.
Exactly. Yeah. Exactly. Okay. So what we have here is that when you transition from one interval to another, because of this level of coarse graining, you enhance spurious fluctuations at the border. So we call this border effects. Okay? So we get unwanted abstract transitions between intervals. Okay? And so what we want to do is to fix this, number one. And so the way that we fix this is by allowing intervals to overlap. Okay? So you will remain in your current interval until you exit from one of the boundary values. And once you enter a new interval, you are no longer near the borders. Okay? You are now somewhere in between two consecutive intervals. Okay? So now you have some work to either go in the upwards direction or in the downwards direction. Okay? So we believe that this should better approximate the underlying dynamics of the system. And actually it does, because as I mentioned earlier, the steady state value is when the value of A is equal to 20. When we abstract this in this context, it's when it's now contained in the blue interval. And now if you look at macro transitions, so interval transition between intervals, it's more likely to converge to the steady state interval, which in the previous case, it wasn't the case. Okay? So if you understood everything up to this point, then I've done my job well. And if not, then I've not done my job well, obviously. Okay? And so now what we will try to do is to derive the language of the formalizations that we do. And the way that we do this is that first we define the concrete semantics, which describes all the behaviors that can emerge from a reaction network, a system of reactions. And then we define the abstract semantics, which is an over-approximation of the concrete semantics. Okay? So we will begin with the first, which is the concrete semantics. And so what we do is we essentially build the mathematical objects that we require to define all the behaviors that can emerge from the reaction network. Okay? So we begin with the first, which is the variables involved, the values they can take on, and this meaning of reaction and reaction networks. Okay? And so here, so I'm not going to go extensively through the definition. You can find it in the paper, but I give you a general overview. Right? That's the point. And so a reaction describes how each variable in the system can participate in a reaction. And each reaction is associated with a propensity. And so you can imagine a reaction network to be a family of reactions. Okay, so it describes essentially how each variable can participate in different reactions and how they are updated. And then what we can do is just define chemical states. And so what a chemical state is a function. And a function maps variables into natural numbers. And you can imagine a state to be a vector, such that each element in the vector contains the value of the variable. Okay? So nothing too complicated. And so what you can do after that is to define chemical transitions. And so a chemical transition is a relation between two concrete states. They are related by a reaction, and you have a predecessor state. You apply a reaction, which you can imagine as a rule. It updates it, and you get a successor state. And what you can further do is measure a probability for each chemical transition. Okay? So a predecessor state is involved in determining the propensity of a reaction, and a probability for a transition is computed by computing the propensity of a reaction and dividing it by all the propensities of each reaction in the reaction network. Okay. And finally, the last mathematical object we require to describe all the behaviors of the reaction network is the set of all chemical traces. And so a chemical trace you can imagine as a pair where you start from an initial state, and what can happen from this initial state is many different chemical transitions. And also for each transition you have probability of the type of transition that can occur. Okay? And to compute the probability of a chemical trace, you just compute each of the probability of each transition along a chemical trace. Okay, so we're done here. And so now what we would like to do is to define the abstract semantics. Okay, so the abstract semantics is an over-approximation of the concrete semantics. And we approximate the chemical values by intervals. So we would characterize these intervals and build a hierarchy of the different kind of mathematical abstract functions that we require to go from chemical values or chemical states into the abstract realm. Okay. And so here, so abstract intervals are sequences of couples. An abstract interval is composed of a lower bound and an upper bound. And an abstract interval represents a range of chemical values. This is how we interpret it. And one further property that we impose is that intervals can overlap. So that means that if you take two consecutive intervals, the upper bound of the first interval is greater than or equal to the lower bound of the next interval. Okay? So you have some region where the intervals can overlap, share some values. Okay? And so in order to go from chemical values into abstract intervals, you need to define the value abstraction function. Okay? So you need to define a mapping from the concrete realm to the abstract realm. Okay? And so here we define a function beta. Beta is parameterized by an abstract interval. And in order to assign a chemical value into a new interval, you assign it by taking the abstract interval that's at smallest distance to your abstract interval. Okay? So we have some notion of whether we remain in a current interval, or if we do enter a new interval, we would keep track of about that information. So it's context sensitive. Okay? And the state abstraction follows from the value abstraction function. So what we do is we first define an abstract state. So it's a mapping from variables to abstract intervals. And then we can define the state abstraction function in a similar manner to the value abstraction function. So the state abstraction function is parameterized by an abstract state. And you can imagine that component-wise, we lift the value abstraction function to each of the chemical values in a concrete state. Okay? And finally, in order to obtain abstract traces, okay, so we define the trace abstraction function. And so an abstract trace is similar in structure to the chemical traces, except that we lose information about probabilities. However, we can propagate probabilities by reasoning on the type of transitions or traces that can occur in a reaction network. So we will do that. So there's more information about it in the paper, but I don't have enough time now. And so to obtain abstract traces, you use a trace abstraction function, which takes as an input a chemical trace. And along each concrete state in the chemical trace, it will lift the state abstraction function. Okay, so nothing too complicated at this level of description. Okay. And so what we can then do is show you another example as to how we can coarse-grain a system that's more than one dimension. So here we have three variables. Okay. and how we can use this framework to automatically generate the discrete models that we would like with probabilities. Okay? So here we have again two reactions. On the left-hand side, you have a reaction that consumes some A and produces some B. And on the right-hand side, you have another reaction which consumes two equivalents of A and produces some C. So you notice immediately that each reaction uses the same resources. Okay? And what we can do is derive the probability functions using the definitions we introduced previously. And then what we would like to do is observe the dynamics of B and C. Okay? So what we can do is, using information about the properties of the reaction network, we can derive a mass invariant since both reactions use the same resources. And then we can substitute this invariant into our probability expressions to observe the dynamics of B and C. Okay? And so the type of phenomena that we want to observe is the ability for the two reactions to compete for resources. So we have two scenarios. In the first scenario, when the amount of A is low, you observe that the first reaction is more dominant. Respectively, when the amount of A is high, you observe that the second reaction is more dominant. Okay? So what you obtain is a 2D abstraction system like this, of the sort, where on the x-axis you have the quantity of B, and now on the y-axis you have the quantity of C, and each rectangle represents an abstract state. And so each abstract states, so the intervals along each dimension are allowed to overlap. You can transition from one abstract state to another, given some interval of probabilities that we can compute using the proposition we defined at the beginning of the presentation. And the general trend that you would like to observe is essentially where these two reactions can converge along its respective axes. Okay? And so what you should see first is all these red crosses. So these are unreachable abstract states. So when the system is completely depleted of resources, the system would deadlock. Okay? And so for the first scenario, what you will observe is that the interval probabilities will likely go towards when the amount of A is much larger. Okay? And in the second scenario, if we tune the amount of A to have, when you start off with a larger pool of resources, first you have many more abstract transitions. Okay? And you will see that the dynamics will converge towards higher quantities of C. And as the amount of resources become depleted, you slowly start to converge towards the right-hand side to prefer the amount of A. Okay? So these are the type of behaviors that we want to capture. And what we show is that we can really build these type of discrete models by reasoning on the reaction network, rather than having to handwrite the logical models to then be able to better capture the underlying process of different types of reaction networks. Okay? So I would like to conclude here. And so short term, what we did was to really propose this generic framework that allows you to build this type of coarse-grained models with probabilities. And then we illustrate this framework in two case studies. Okay? So you can imagine now that the long-term goal would be to continue to reason on the type of properties of the reaction network to obtain, of course, more precise abstractions. And then we would like to illustrate our framework in systems that contain many more variables, for example, and try to perform some kind of approximation schemes that allow us to reason a bit better on the type of model reductions that we can do from large systems of reactions involving many variables. And with that, I would like to thank you, and I'm willing to accept any questions. No questions? Okay.
So maybe I can begin a stupid question, but does it make sense to consider some different abstract domains, for instance, not just intervals like polyhedra, for instance, want to compare different chemical traces, maybe not in this model, some other models?
So yes, it is possible. So for example, you can use some kind of integer linear programming constraints, which are maybe composed of inequalities. And if you abstract using the inequality domain, the abstract inequality domain, then you can, you can use this kind of constraints to refine the abstract domain and be able to, for example, if you observe the dynamics and the dynamics occur within some kind of regime or some kind of region, you can use these type of inequalities to refine your abstractions. So yes, it is possible, but I am not there yet.
Yeah, I understand. It's first steps, towards, right?
Yeah, yeah.
I have a question.
Okay. Okay.
So I would assume one of the properties you would like to observe at the end when you have the abstract traces is some for other sets of chemical reactions, like oscillations and stuff like this. But do you think my feeling is that you have maybe lost too much information about the timing in the abstraction process to get more insights about like the periods or things like this.
Yeah. So that's a nice question. So in this context, we do not care about time because we want to have a framework that we can use to assess logical models where the notion of time is already abstracted. So what we use is a discrete time Markov chain, which is similar in structure to the logical style of modeling. And so I think you're referring to like continuous time Markov chains where you examine probability distributions between reaction events. But in this framework, we don't use it because we don't need it. A discrete time Markov chain is enough to assess the kind of properties we're trying to observe. Yeah. And also the discrete time Markov chain simplifies the mathematics significantly.
Yeah, sure. But do you think you could recover some kind of information based on the abstraction?
What kind of information? So I don't really know. So it depends on the type of question you are answering. And so for the type of question we are answering, which is really assessing the behaviors from the logical models and allowing, for example, reversible transitions between abstract states and examining probabilities between abstract transitions, it allows us to better assess the type of behaviors that can be ignored in logical models, whereas in our framework you can obtain these kind of models from the reaction network itself. So you have a little bit more confidence in the type of discrete models that you produce. So maybe for another question, yes, but at the moment we don't think about this.
Okay, thanks.
Yeah, thank you. Yeah.
Great talk, thanks. I wondered, how do you test these properties in the lab in terms of like not mathematical model, but basically try to test out your theory about biological models on these using these formulas. So how do you make sure you're going in the right direction? Because it sounds hard to model a model like this out of the blue without really making measurements. So
I ran away from the lab a long time ago. But so the way that you would do this experimentally is that you can imagine that each reaction represents a process. And so maybe this is a process that you will try to calibrate in a lab. So for example, if you have a protein that's responsible for consuming a sugar, maybe, you can measure the rate at which this protein consumes a molecule. You can try to provide controlled conditions for this to happen, and then what you can do is really calibrate the reaction rate of this reaction. So maybe you can do this for a few reactions, but if you have a system of 500 reactions, it's very difficult or impossible. And so what we would like to do is not only to provide more like a rigor, not only to provide a tool where you can build more confident models, but when you do learn information about certain reactions, you can implement this into the model and calibrate it accordingly. So of course, if someone does the experiments, you can then use this framework to plug in the values of the experiments you did, and then be able to get more larger models, for example. But at the moment, it's very difficult. So it's I don't know. You kind of have to build your models very carefully, and I think you see where I'm going with this.